Welcome back, everybody. Today we're going to talk about confidence intervals for a population proportion. In our last few lectures, we talked about confidence intervals for population means. We started by considering a confidence interval for a population mean with the unrealistic assumption that we knew sigma, the population level standard deviation. While unrealistic, this was an informative example, really just designed to help bridge the gap between the central limit theorem and where these confidence intervals come from. Hopefully it gave you an intuition for how confidence intervals work and why they work. Pragmatically speaking, though, we really only care about two different types of confidence intervals. The one we went over in our last lecture. This is an estimate for a population mean, where we drop the assumption that we know the population standard deviation. Not only is this more realistic, but this is the one that you actually see used in practice by researchers. The only limitation here is that it only applies to one type of parameter estimation, right? So this is only working for population means. So I can estimate the mean income, or I can estimate the mean age in a group, but I can't use this approach to say estimate what percentage of the population has blue eyes. To do that, we need to consider a different confidence interval, one that estimates a population percentage. Our work in the past lectures are still going to pay off for this new type of confidence interval because the steps are more or less the same. We're still going to compute some information from some example data, we're still going to compute critical values, and we're still going to put together a margin of error that we're going to move away from some sort of best guess point estimate. So the steps will be pretty much the same. The only difference is we're going to have to make certain modifications so that we're estimating a population percentage rather than a population mean. Let's consider some things moving forward. First, let's set some notation. Our parameter, we're going to denote with a little p, and I'll typically put the parameters in green as you've noticed in the videos. So p is representing the population percentage or proportion that have a certain characteristic. I'm just going to think of this as they said yes to a survey question. But this could be anything. It could be they have blue eyes, they scored 70 or above on an exam, etc. Now, when we actually go out and collect data, and then we compute the percentage in the sample, right? This is something we call the sample percentage. We have to differentiate that from what's happening in the population because they're two different things. The sample percentage is just a small little snippet of what might be happening in the population. So the way we denote this is with a p, again, for percentage or proportion, and we put a little hat on top of it to indicate that it's coming from a sample. So we'll refer to this thing as p hat. And this is, again, the percentage in the sample, not in the population, but of the sample that we collected that have the characteristic that we're interested in. In this case, saying yes to a survey problem or a survey question. A couple of key points to keep in mind. First, we're no longer estimating a population mean, so we're going to have to make some changes. But more importantly, the data that we're going to collect is going to look different. We're probably going to see a list of maybe survey responses. This will be more categorical level data more than likely. Rather than using the t-distribution, as we covered in our last lecture when estimating a population mean with a confidence interval, we're going to go back to using the z-distribution, the standard normal distribution, when we look for finding our critical value. P hat, our sample percentage, is going to be our best guess for what the population percentage is going to be. This is similar to our sample mean being our best guess for the population mean. And as such, we're going to use p hat to be the center of our confidence interval. Finally, our margin of error formula is going to change significantly from what we've seen in the previous examples. This is because we're using a different sample statistic to estimate a different population parameter. So we'll try to develop some intuition for how this happens by showing you a couple of visualizations. The first visualization I'd like to show you is very similar to the one that we had for population mean confidence intervals. In this case, our setup's a little different. So what you can see over here in the left-hand panel, this is a population of people, and they're colored either red or blue based on whether they're a positive case or a negative case. So you can think of maybe the blue dots are people who said yes to a survey, the red dots are people who said no. We can change this if we want So we can kind of play around with this, which maybe we'll do in a future video. But for now, we're going to set the population proportion to be 0.4. So this means 40% of the dots in our population are labeled with a blue. We're going to fix a sample size, let's say 25. And basically what happens here is when I click the Get One Sample button, it's going to take a random sample of 25 of these dots from the population, and it will automatically compute the sample percentage that are blue. So in this case, we've got 0.36 for the 25 dots that are kind of highlighted here by circling them in black. You'll notice we have some blues, we have some reds, and in general, the percentage that are blue in the sample is 36%. Okay, we can get a couple of other samples here. We'll notice that generally speaking, the dots in the middle of these confidence intervals, these are our actual sample percentages. This is what we call the point estimate. This is our best guess for what the population percentage is going to be. In one case, it actually seems to come very close to the actual population percentage, but generally speaking, it's near but not exactly equal to that population percentage. So far, though, for the 6 confidence intervals that we created by doing 6 different samples, our success rate's been 100% for the interval, right? So 100% of the intervals so far have overlapped with the true population percentage. Now, if we collect more and more samples, you'll notice that certain intervals, right, certain unlucky samples pulled from that population end up leading to a confidence interval that doesn't intersect with that population proportion, right? So these are, unfortunately, confidence intervals that fail to actually capture that population proportion. However, you'll notice that having repeated a bunch of times, we do have a notion of a success rate. So thus far, 95% of the confidence intervals we did generate ended up overlapping with that population parameter, the population proportion. And so essentially we can kind of model our success rate by thinking about in the long term, right? As we collect hundreds and thousands of different possible samples from the population, how many of them led to a successful confidence interval. And this success rate is what we start to call the confidence level for our confidence interval process. Right? And this is very similar to what we saw with our example with population mean estimates using a confidence interval.